Hello students, welcome back. In today's class, I will be starting another chapter, that is photoelectric effect. Now, according to the syllabus, we are left with only two chapters, that is photoelectric effect and matter waves. Now, this chapter is chapter 23 from the unit that is dual nature of radiation and matter. Now, first of all, I'll explain you what is photoelectric effect. The phenomenon of emission of electrons from metals under the effect of light is called photoelectric effect. Now, we have got a metal plate. Suppose a light falls on a metal plate, then what happens is the electron present in the metal plate will be ejected. So this effect of removing the electrons from the metal under the influence of light is known as photoelectric effect. Now this phenomenon was first observed by scientist Hertz. What he observed was when UV rays are made to fall on the negative plate of an electric discharge tube. Now discharge tube means we take two plates, one is negatively charged, another one is positively charged. It is kept under vacuum. Okay, this is zinc plate kept under vacuum. Now this is connected to battery, which is providing some potential difference, and a galvanometer from where we can see if the current is flowing in the circuit or not. Now what he observed was when the UV rays was made to fall on this zinc plate kept in the vacuum, the electric discharge becomes easier. That means some amount of current it was flowing. Now the current which was flowing was shown with the help of a galvanometer, which shows the deflection, which means that there is current in the circuit. Now when ultraviolet rays are made to fall on the negative plate, immediately the current starts flowing in the circuit. As soon as the ultraviolet rays are stopped, the current stops flowing. If on the other hand, the ultraviolet rays are made to fall on this positive plate, no current flows, or very feeble current flows. Now this was observed but could not explain this phenomenon. However, Hertz and another scientist, Holowach, couldn't explain this phenomenon. Afterward, J.J. Thomson established that when light falls on the metal surface, electrons are emitted from the surface. Leonard told that when ultraviolet rays fall on the negative plate, the electrons emitted from the plate are attracted by positive plate, so the circuit is completed and current flows. So when it falls on negative plate which has got excess of electron, the electron will be ejected and the circuit will be completed and the current flows. But if the rays fall on the positive plate, if the UV ray fall on the positive plate, the electron emitted from the positive plate do not reach negative plate, because this is negatively charged plate. When electron which is negatively charged try to go to negative side, then negative and negative will be repelled. That is why the circuit won't be complete and the current will not flow. So the phenomenon of emission of electrons from metal under the influence of light, UV ray is light, then this is known as photoelectric effect. The electron which is emitted are known as photoelectrons, and the current which flows from positive to negative, this current is known as photocurrent. For this phenomenon, the light of short wavelength is more effective than the light of long wavelength. So UV rays is effective. The same experiment was performed by Hertz and Leonard together on photoelectric effect. So I'll show you the setup of that one. Okay, now this is the setup for Hertz and Lennard's observation. What they did was, they took two plates P1 and P2, kept in vacuum where light could fall on this. Then this is connected to an ammeter to see the amount of current, connected to commutator where we can change the circuit, the flow of current. Potential divider actually we can give the amount of potential or increase or decrease the amount of potential, and a voltmeter to see how much potential difference is there in the circuit. Now what he observed was, when light rays of definite intensity, intensity of light can be changed, and a definite frequency fall on a plate P1, then photoelectrons are emitted from P1. Electrons are emitted from P1 if the plate P2 is at sufficient positive potential. So how can we change the potential? Now if this 1 and 1 is connected, then what happens? P1 is at negative potential, P2 is at positive potential. So when P2 is at sufficient positive potential, then all the photoelectrons from P1 reach the plate P2 and maximum photoelectric current flows in this circuit. On increasing the positive potential, now potential can be increased using the potential divider. Now on increasing the positive potential of the plate P2, there is no increase in the photoelectric current. So on changing the potential, there is no change in the current, because all the electrons emitted from plate P1 has already reached plate P2. If however we double the intensity of the falling light over here, if you increase the intensity of the light on the plate P1, the photoelectric current is also increased and it becomes double. This means that photoelectric current or the rate of emission of photoelectrons is directly proportional to the intensity of the incident light. So if we draw a graph between photoelectric current and potential, the graph will look somewhat like this. Okay, if we draw a graph of potential difference and photoelectric current, x-axis is potential difference, y is current, this side is negative potential, this is 0, this side is positive potential. Now suppose if you have a light of intensity I, then this will be the type of graph. Intensity is I. Now suppose if you increase the intensity of the light, then what happens? Current will also increase. This is when we make double intensity. Intensity is twice I. So if you increase the intensity of the light, the current is also doubled. You can see from the graph, the current is also at higher level. This is what happens when we increase the intensity of the light, and the dependence of the current and the intensity is directly proportional. Okay. Now if we change the commutator, now by inserting the plugs in the gap 2 and 2 of the commutator, we give P2, and this P2 will be negative, potential will be negative, and P1 will be positive. So instantly what happens is, when we connect 2 and 2, we give plate P2 a negative potential relative to the plate P1, then the current immediately decreases but does not become 0. This shows that electrons emitted from P1 have kinetic energy. On increasing the negative potential of P2, the current falls rapidly and finally becomes 0. At this stage, okay, when we make this a negative potential, the current becomes zero. We can see from the graph itself. Okay, we can see from the graph itself. On increasing the negative potential at P2, the current falls and becomes zero as kinetic energy of electron at this point is not sufficient. So from the graph, what you can see is the current, this is the potential difference when it becomes zero. Okay. At this stage, even if you increase the intensity of the light falling on P1, plate P1, the photoelectric current is not obtained. This shows that P1 emits electrons of different energies. When the plate P2 is at a small negative potential, it repels the electron. Therefore, the electrons with same kinetic energy do not reach the plate P2. So the current decreases. As the negative potential of P2 is increased, the number of electrons reaching P2 goes on decreasing. So the electron goes on decreasing, current will also decrease. The current will decrease slowly. Finally, at a certain negative potential, even the electrons of highest energy are not be able to reach the plate P2. The photoelectric current now becomes zero. The negative potential of P2 at which the photoelectric current becomes zero is called stopping potential or cutoff potential. Since the stopping potential stops the maximum energy electron, it is a measure of kinetic energy of the electrons. If the stopping potential is V0, in this graph, when the potential difference becomes zero, this is the stopping potential. No more further electrons can move. The maximum kinetic energy, let it be Ek, of the electron will be given by E into V0. This is the charge of the electron. This is the potential of the electron. This is the kinetic energy of the electron. Now, if I draw a graph of intensity and photoelectric current, okay, dependence of intensity and photoelectric current, okay, photoelectric current, then the graph will be like this, a straight graph. So the maximum kinetic energy of electron depends upon the potential difference. So this is the frequency. In this graph, the frequency of the light will be constant. Okay, this observation is when in this graph the intensity of the light is fixed. That means the frequency of the light is not changed. Okay, if you decrease, or the previous graph which I have shown you is when the intensity is being changed. Okay, this graph is when intensity of the light is different. Over here, even though the intensity is different, over here the frequency of the light is constant. Frequency is same. So for a certain frequency, this will be the graph. Okay, this will be the graph for a certain frequency. Now what happens if the frequency of the light is changed? If at the stopping potential, light of different frequency higher than the frequency before be made to fall on P1. Okay, if at the stopping potential, when there will come a point that is known as stopping potential, when no more electron will be moving from one plate to another. So at that point, what if we make light fall over here that is of different frequency than before? Then the photoelectric current will be re-established. That means the current will start flowing again. On increasing the negative potential at P2, the current again stops. Okay, so if we change the frequency, then what we can see is again the current is flowing. This shows that higher the frequency of the incident light, higher will be the maximum kinetic energy of emitted photoelectrons, or higher will be the stopping potential. If using light of different frequencies, we plot a graph between the maximum kinetic energy of the photoelectrons and frequency of the light, then a straight line is obtained. Okay? Then a straight line is obtained. So if you draw a graph of frequency, this is frequency on x-axis and y-axis is the kinetic energy or maximum kinetic energy. This is maximum kinetic energy. The same graph is there in the book also, you can follow the graph. So if this on x-axis is frequency, y is kinetic energy, then the graph will be a straight line. Okay, it will be a straight line. Over here is the stopping potential. And if we extend this backward, we'll get this point. Suppose this distance is minus b. So I'll tell you what this b is. Now if you draw a straight line graph between energy, kinetic energy and frequency, it extends backward. It intersects the frequency axis at a point nu naught and intercepts the energy axis at point minus b. This means that for the photoelectron to be emitted from a given metal plate, the frequency of the light incident on the plate should be higher than mu naught. So for electron to be emitted, the frequency of the light should be higher than this. This is the minimum frequency. If the frequency is lower than nu naught, no photoelectrons will be emitted, whatever be the intensity or duration of light. So the frequency has to be this. On the other hand, even if a dim light, okay, with a very low intensity of frequency higher than this is sufficient for the emission of electron. The lowest frequency of the light which can emit photoelectrons from a material is called threshold frequency. So this nu naught is known as threshold or cutoff frequency of that material. So from this graph, the equation of energy can be, energy is, if you draw a slope of this graph, I hope you know how to draw a slope, that is A, slope into frequency minus B. B is this minimum energy. This equation is an experimental result. So this experiment has been performed with the light of different frequencies, okay, light of different frequencies, and this equation has been obtained. So that part is not important. Now next, we'll discuss about, okay, before starting a new topic, I'll just tell you what these things are. This is kinetic energy, A is the slope, this is the frequency, and B is known as the work function. Work function is actually the minimum energy required for the emission of photoelectron from a metal. Is called the work function of that metal. Now it depends, this is known as work function. Now this B depends upon different types of material. For most of the metals, the work function is of order of few electron volt. This is also the value of work function for the emission of thermions from the metal. Now the law of photoelectric emission. I'll just read it out, few laws which was observed after this experiment. Okay, after this experiment, Leonard and Millikan gave the following laws on the basis of experiment on photoelectric effect. The first one is the rate of emission of photoelectrons from the surface of the metals varies directly as the intensity of the incident light falling on the surface. So from the previous graph, I'll show you the previous graph, but it can be seen that the electrons which is being ejected from the metal plate depends upon the intensity of the light, and this one is the graph. This one is an important graph. This is between intensity and potential difference and current. With the increase in the intensity, current also increases. This is the first law. Second is the maximum kinetic energy of the emitted photoelectron is independent of the intensity of the incident light. So the kinetic energy of the electron does not depend upon the intensity of the light. It is independent. That is the second one. Third one is the maximum kinetic energy of the photoelectrons increases linearly with the increase in frequency of the incident light. So the graph of kinetic energy of electron is this one. The kinetic energy increases with the frequency of light. If the frequency is changing, kinetic energy also changes. If the frequency of the incident light is below a certain lowest value, then no photoelectron is emitted from the metal. So if the frequency is below this nu naught, then no electrons will be emitted. This value is known as threshold frequency, which is different for different metals. Fifth one is, as soon as the light is incident on the surface of the metal, the photoelectrons are emitted instantly. That is, there is no time lag between incidence of light and emission of electron. So it doesn't take time. As soon as the light falls on the metal plate, electrons are emitted. Now, the failure of this experiment. The failure first reason is, according to the wave theory, the energy carried by the light beam is distributed uniformly over the wavefront and is measured by the intensity of the beam. Thus, when light falls on the metal surface, the energy of the wave should be transformed uniformly to the electron in the surface before they are emitted out. Okay, so when the light falls on the metal plate, the energy from the light, which is in the form of wave, the energy has to be distributed equally amongst the electron. The energy taken up by the electron must increase as the intensity of the light is increased. Okay, so if the intensity is increased, the energy should also increase. Now this is against the experimental observation that the maximum energy of the emitted electron is independent of the light intensity. So whatever we have observed right now is that the maximum energy, kinetic energy of the emitted electron is independent of the intensity. So that is what we have observed right now. But according to the wave theory, the kinetic energy should be dependent on the intensity. That is the first failure. Second one is, the wave theory suggests that light of any frequency, however low it is, should be capable of ejecting electron from the surface, provided only that the light is intense enough. So any frequency should be able to eject electron. That is according to wave theory. But experiment, however, shows that light of frequency lower than the threshold value cannot eject photoelectrons, no matter how intense it is. So wave theory and the experiment over here doesn't match. Third one is, according to wave theory, the energy transferred from light waves is not gained by a single electron, but is distributed among all the electrons present in the lighted area. The energy has to be equally transformed. Therefore, some time will be elapsed before an electron collects sufficient energy for emission. So when a light falls in a plate, it takes time for energy to be distributed. Then only the electron can be ejected. So it means that there must be some time lag between the incident of light radiation and emission of photoelectrons. But this is against the experimental results. Now this experiment tells us that as soon as the light falls, electron moves out. But according to wave theory, it takes some amount of time for electron to fully absorb the energy, and then only it can eject. So this is also not matching with the wave theory. Thus, wave theory fails in explaining the experimental observation regarding the photoelectric effect. So this theory has been corrected by another scientist known as Planck, and afterward it was Einstein. So about Planck's hypothesis and Einstein's explanation, we'll do that in the next class. I hope it is clear till now. If you have any doubt, please do ask. Thank you for today.